My name is Hazim Gaber, and today we're going to be discussing digital signals. Yesterday we talked about analog signals and how we can measure them. So, if you recall from before, the analog signals we're looking at are sinusoidal. So, if I'm going to take the signal as an amplitude, remember, and this is time. So if I take a section of the signal and draw it here, so let's say this is from 0.5 seconds to 0.6 seconds. Imagine I want to measure the value of our signal here, and here, and here. So here it might be, assume the amplitude is 1. So here it might be 0. Here it might be negative 0.5. Here it might be negative 1. So I guess the point is, if I took some more measurements, I could be here at 0.25, and here is negative 0.75. And I could go on. I could take even more measurements. But what we're saying here is this signal is infinite. I could measure it forever. I could have an infinite number of measurements. And if I were trying to convert this analog signal into a digital signal, what I'd have to do is measure it every so often. And the rate at which I measure it is called the sample rate. That's very important, because the question is, if you look at a digital signal is off and on. So that's all you get. It's either on or off. So how can I convert an analog signal into a digital signal? What sample rate should I use? How often do I need to measure my signal so I can create an accurate digital representation? Because a computer can't store this signal to an infinite level of precision, because it would take all the memory in the world to store an infinitely small piece of the signal. Because, I mean, imagine what is the largest sample rate you could have. Say I measured it once per second, or 10 times per second, or 100 times per second, to measure an infinite number of times per second. So just this tiny piece could measure an infinite number of times. And that would mean I have an infinite number of measurements. And that would mean I need an infinite amount of space. So, but there are some strategies here to think about. And what I will say is, first of all, we need to know what is our signal representing. And by the way, this is now third year electrical or mechanical engineering subject matter. But we know we have a frequency for the data. So voice, video, etc. And we can filter frequencies that don't match. So, and then our sample rate should be 2 times the frequency. So if our frequency is 4 kilohertz, then our sample rate can be 8 kilohertz. And this ensures that we don't miss any data. Because what happens if this is my curve and I take a measurement, this is my frequency here. So, and I take a measurement here, and then take another measurement here, I'll miss out on all this data. So that's a bad idea. Now, the last step is remember that this amplitude represents something. And so if this is 0 and this is 1, we would probably create a table and just go data and then actual. So if we went from negative 0.1 to negative 1, negative 0.9, negative 0.8, all the way to 0, and then 0.1, 0.2, all the way to 0.9, 1.0. Let's say this was an image or a video signal. So the signal is telling us the color of a pixel, 1 pixel at a time, and we have 64,000 colors. So this analog signal may be representing an observed color and an observed pixel, and so we could convert this. So actually, I would have many more values here than what I've drawn. I've only approximated 20 values, but let's say that this end is reds, all the Roy G. Biv, so reds, orange, yellows, greens, blues, indigos, violets. In other applications, though, this could be a temperature sensor, audio. So if this was a temperature, this might be negative 270 degrees, and this might be positive 500 degrees, and this would be 0 degrees. So say I measured here, say my measurement was right here, and it was 0.5, I might approximate that to 40 degrees. So the point is, we gotta convert the value of the analog signal to a value that the computer can understand. Because this signal doesn't mean anything. It may have a fixed amplitude and we're just changing the frequency. Or it may have the amplitude may not directly correspond to what it's measuring. So we just need to convert. And this may be a linear representation, or it may be logarithmic, or it's gotta make sense. That's the point. And once we have that, then we can understand, we can make sense out of our data. So you might choose to have increments that are, a multiple of like 2 or 256, but you don't have to. And so there's actually some algorithms in use to make sense of data. And one of them is called PCM, or pulse code modulation. And the way that it works is it's 256 levels. So this is our signal. And this is at the top. This is 1. This is the bottom. And here's 0. So when we measure, and we might measure this more often, but every value we get is going to be rounded to the nearest 1 to 256. So here would be 256, and here would be 0, and here would be 128. And so, this might be 75, and this might be 200. So every measurement we take, we're going to assign it a level. And we might get 2 measurements that are pretty close. So let's say, for the sake of argument, this was actually negative 0.5. This was negative 0.495. We might approximate both of those on our scale to 75. So now I've taken a bunch of measurements, maybe 0, 0.1, 0.25, 0.38, 0.5, 0.7, 0.9, 1, 0.7, and then I'll approximate these to 128, 130, 256, 250, 230, 200, 180, whatever, 230. So we gotta choose a scale depending on what precision we're trying to convey. Because I might say, why don't we make a scale that's between 1 and a billion? But if this is measuring, audio volumes, do we really need that level of precision? Because in order for this number to be precise, this number has to be precise. So in order for this number to be precise, really precise, we need to have really high quality measuring equipment. And that equipment's expensive. So, and the end result is data that's very precise, but it may be a level of precision that has no use to us. Because, like, say we're measuring the temperature, we might, if it's temperature, we might only need to be within 0.5 degree Celsius. So do we really need to know that the room temperature was 28.37964 degrees, or are we good with 28, 28.5, etc.? Same with volume. Do we need to know that the volume was 8.275 decibels? For recreating the sound, a human ear can only understand the difference between, say, 500 or 1,000 levels of volume. It may not even be that high. And the reason 256 is such a special number in computing is because we can represent it with one byte. With one byte. Because recall, a byte is 8 bits. So if I have all 8 bits, remember that a byte is made up of 8 bits, which are off or on. So I won't go into detail here, but basically, computer can count on one byte the numbers from 0 to 255. So that's 256 different numbers. And it can do so by setting the value of each bit to either 0 or 1. In this case, if we set all, so the first bit is worth 1, second bit's worth 2, third bit's worth 4, fourth bit's worth 8, the fifth bit is worth 16, sixth bit is worth 32, the seventh bit is worth 64, and the eighth bit is worth 128. If we set all the bits to 1, we get 255. By way of example, if I set 1, 1, 1, 0, 1, 1, 0, 1, for example, now I don't have 2 in here, I have 16, so I have my number now is 128 plus 64 plus 32 plus 8 plus 4 plus 1, which is 238. So no, it's not right. 55. 237, right? Yeah, 237. So the point is, I can make any number from 0 to 255 using the system. So based on that, so now looking back at our analog signal, which has 256 levels. So every piece of data we sample can be represented by a number which is actually 0 to 255, where each sample is 1 byte in size. So say this was a 4 kilohertz feed, so we need to measure twice the feed maximum. So 8 kilohertz, so that means we're measuring 8,000 samples per second. And each sample is 1 byte times 1 byte per sample. So we cross out the samples and we get 8,000 bytes per second. for 8 kilobytes. So that's our bit rate. Our bit rate is how much data is coming through. We can have bit rates in bytes per second, or kilobytes per second, or megabytes per second, or gigabytes per second, or terabytes per second. So typically audio, the voice, is between 16 and 64. And we also have ways to compress this if needed. So with that in mind, we also have another idea which we call TDM, or time division multiplexing. Because what happens when I've got a bunch of different datas coming in, and say this is like a telephone switch somewhere, and I have a huge line to another central office. I want to take all of this data from different sources and shove them down one line. How do I do that? And the answer is we do what's called time division multiplexing. So that means I'm getting a ton of data, but I don't need to listen to all of it. So if I take a sample of each data, let me change this. So I'm going to sample each data at a different interval when it comes through. Because remember, we don't need all the data anyways. And then I'm going to take the data one at a time. So now I'm going to take the green one. And then I'm going to take the red one. So I've left a huge space here between my samples, but now on my main line, I just have a very small space. So if you think about it, my line's going to end up looking like this. Because I'm going to take another data, another data, another data. Oops, should be blue. So you get the picture here. So basically what we're doing is we're giving each data feed some equal time on our stream. And as long as our samples are frequent enough, we're not going to miss any data. It's like if you've got 3 people talking and you're jumping from one conversation to the next to the next. If you spend, a second here and a second here and a second here, a second here, second here, second here, you might pick up enough information to make sense out of everybody. But if you spent 15 minutes here and then 15 minutes here and then 15 minutes here, you're not going to make any sense, because you're going to lose 15 minutes of data here. In our case, of course, we're sampling thousands of times per second. So even if you heard the 1/60th of the data, you're hearing it often enough that you get you have minimal data loss. So little that people don't notice. So the way that TDM works technically is with a more complicated algorithm that kind of predicts which streams get which space. But we want to make sure that we sample each person. And so we have a TDM frame, which is known as the DS1. And this contains the data. So we have one bit. This is a frame bit. And then we have our channels. So channel 1, channel 2, all the way to 24. So we can carry 24 streams of data within our frame. And this is 8 bits. So we can take this whole frame and transmit it down our line with 24. So we get 24 samples from 24 different sources, and we merge them together. So if you think about it, as I said earlier, we have a 4 kilohertz voice, which is 8,000 samples per second. So what we need is 125 microseconds per sample. So every 125 microseconds, we're sending another sample. And it's 8 bits, right? Because it's one byte is 8 bits. So every 125 milliseconds, each item is filling up the frame. Now, here's where it gets interesting, because if I took my 8-bit frame, my 8-bit sample, and I multiply by 24 samples, I also have 1 framing bit. So 24 times 8 is whatever it is, but 1 frame bit what's 8 times 24? If I power on my calculator. It's been a while since I used this, but it's 8 times 24. There's 193 bits. 193 bits per DS1 frame. And remember, we're sampling 8,000 samples per second. So we take 193 bits per frame times 8,000 frames per second. We get a very interesting number of 1536000, which is actually turns out to be 1.544 megabits per second, which is the speed of a T1 line. How do I convert this to this? Well, there's 1,024 megabits per byte. Anyway, oops. I made a typo here somehow. Scratch all that. So this should have been 1544. I must have pushed the wrong button on the calculator. Anyways, so yeah, so this is our T1. The T1 can carry 24 voice channels at a sample rate of 8,000 per second. Now in Europe, they use a PCM30, which is 30 channels to 24. But theirs is a weird system. So their frame, just do this on the next slide. Europe has 32 channels. So it's got an 8-bit signal, and then channel 1, channel 2, channel 15, etc. And then you have an 8-bit signal, and then channel 16 all the way to channel 30. So you have 30 data plus 2 signal. That's 32 channels. 32 times 8 bits times 8,000 samples per second gives us 2048000, or 2.048 megabit per second. Now, you're probably wondering, and we can do this, we can take a bunch of T1s and we can merge them and end up with a really big frame. And now we can multiplex multiple T1s. So 4 T1s makes a T2, and 28 T1s makes a T3. So that gives us our T3, which is 43.232 megabits per second. When I was learning, I thought this was fast because I had dial-up internet, and my internet was like 4 kilobits per second. I was lucky. Now on the other end, of course, we're gonna split these back up. So we call this multiplexing. And on the other end, we have the multiplexing. So in order for us to get a voice channel out of our T1 here, we have to demultiplex and then extract our channels. So this massive frame, if we have 12 T1s, we call that a super frame. Or 24 T1s, call that a extended super frame. In Europe, it's 16 E1s, call that a multi-frame. So, but how do we actually send this data down a router? Because remember, we have our binary signal, and it's gonna look like this. Scratch that. It's gonna look like, it's not gonna have different heights. It's gonna look like this. Zeros and ones. I mean, even this part isn't actually. So how do we do that? How do we get? So remember, we went from this wave to a table with a bunch of numbers based on our samples. And then we went from this table to this frame, which contains data from multiple streams. So this one went into here. This data went into here. And then we combine all of these multiple frames into one big jumbo super frame. And now we want to convert this whole thing into 0, 1, 0, 0, 1, etc. How do we do that? Because what ends up happening is on the other end, we're going to get a signal like this, for example. But these are just electrical pulses. So this recipient is listening to see whether the value is going to be 0, value is going to be 1. But there's always noise on the line. So the noise could mess up our signal. It can mess it up a little bit or it mess it up big time. So we might end up with a signal that's not, perfect. So, for example, if I had an electrical signal and there's a slight bit of voltage here, is this a 0 or a 1? And then, what if this distance, how many, is this 1 0 or 2 zeros, etc.? How do we know? How do we measure this? How do we make this signal? How do we make this signal so perfect that there's no ambiguity on the other end as to what it is? And there's a couple of ways. One is we're going to try to shape the electrical pulses so that we limit the frequency. And one way that we do that is we have different pulses for ones and a complete 0 level for zeros. So if I have, so to answer this question, how do I know how many zeros I have? And the answer is we use something called bipolar alternate mark inversion. Also known as AMI. We also have another technique called Manchester. Coding. So what we do is rather than have a bit that's just positive, it'll be positive for half the signal and negative for half the signal. And so our transition to the next bit happens in the middle. The bipolar system uses a specific pattern for each bit, for a 0 bit. So, and I ripped this off Wikipedia, but let's take a look here and say this is my clock. Oops. So every time interval, this is another, we're taking a measurement of our signal. So in this case, our data is 1, 0, 1, 0, whatever. Instead of, with AMI, instead of staying positive, we alternate. And so we go to, so this one is positive, and then our 0 is 0, and then our next one is negative. So notice here, we have 3 positive bits in a row. We could have a problem here because the computer will just see the positive signal for a while. It's not going to know how many ones we have. It might assume this. This might look like a single positive bit, but with AMI, if we've encoded our 1 is positive, and our next one is negative, and our next one is positive, we now have changed the signal 2 times, so it'll be pretty obvious to the computer that 3 separate bits have been received. And then we go back to 0. The other benefit of this is we can remove the DC voltage, because DC voltage builds up in the line. And so if we have a buildup, our 0 might look like this. So this isn't good because the computer might interpret this level as a 1. But we can remove the DC voltage and not have this issue. So there's a few things we can do here. So at our simplest digital signal, we call we have a technique called polar non-return to 0. And the way it works is we never have a 0 voltage. So we either have a negative voltage or we have a positive voltage. And so our signal looks like this, where these are 0s and these are 1s. And we're measuring against the time. the second method is what we call a bipolar AMI. And bipolar lets us switch, as I said, locations. I mean, switch voltages. So in this case, we have three positive ones in a row. If we ran the positives as a straight positive voltage, the computer might not sense that these are three distinct positive bits. So what we do is we give it one positive, one negative, one positive, where we set 0 to positive. And now we have three separate voltages, two separate voltages, but three signals. We've changed the voltage twice, so it's really obvious that we have three 1 bits. And then we have what we call a Biphase Manchester. And the way that works is we have, again, we never have a 0 voltage. So our signal looks like this. And the way this works is a computer checks. So this is a 0. And the reason this is 0, so if we cut this, we'll do this again. So we have what's called a biphase Manchester. And remember, we have a clock. So if we change phases, there's a positive, negative. If we change phases once in our cycle, that's considered positive. And if that's considered 0, and if we change phases twice, it's considered a 1. So in this case, change phases once in a second, so 0. If we change phases twice, that's a 1. So this is a 1. We call it a 2-state. And then we can also try to encode 2 bits into one stream. So 2 positive bits is 1, 1, which is the full voltage. 1 positive, 1, 0 gives us a positive third of the voltage, and then 0, 1 gives us a negative third, and 2 negatives gives us negative voltage. So that results in a more complicated, so this is 0 V, and this is plus V. This is plus V over 3, minus V over 3, minus V. So if we have a voltage looking like this, for example, so now here we can interpret this as 0, 1, interpret this as 0, 0, interpret this as nothing, can interpret this as 1, 0. Should never have drawn this. This should go straight through. So 1, 0, and then 1, 1. So now our stream is 0, 1, 0, 0, 1, 0, 1, 0, 1, 1. This is also known as 4-state. There's a few other ways of encoding. One's called QAM, or Quadrature Amplitude Modulation. And in that case, we have two sine waves, and they're off by a quarter of a phase. And then, so this is technically sine t, and this is cos t. And we can combine these two waves, so we end up with a sine wave and a cosine wave. When you add these up, you end up with a flat line here. And then yeah, you end up with something like a signal like this instead, because we're adding peaks and valleys. So here, remember, here we're positive and here we're 0. So anyways, this is not totally correct, but basically we end up with a wave like this, and then we can call one of these the I signal, and one of these the Q signal, and these are combined to make one signal, which are transmitted, and then the receiver demodulates these back into the original waves. So I guess the takeaway is we can convert an analog signal to digital, and then once converted, we can transmit our digital signal long distances with minimal noise. An analog signal has a lot of noise, and we can convert our digital signal back to analog if we wanted to, but there's some data loss. But going back to our sampling rate, with good sampling, loss is negligible. And digital signal has no loss. Any questions?